Okay, 20.4, carbonyls as electrophiles. And this probably, you're used to seeing these sections as properties, right? That's what you're expecting to come next because you just saw some reactions, properties. So the next couple sections are dedicated to the properties here. And folks, let me emphasize, this is a big deal. This is going to fit nicely into what you learned in Gen Chem, but more importantly, it's going to help you understand what's going on here. Oftentimes I use an example of counting when I first start a semester or a professional work with organic chemistry students, because counting is not a big deal, right? I had a little girl a few years ago come up to me and say that she could count. She wanted to count for me. And it was delightful for me. It was my little girl, right? My daughter. It was delightful for me. It was lovely, lovely, lovely. And she counted all the way up to 38 and stopped. And it was remarkable to me that she could get, first of all, it's remarkable to me she could get that far. When you're a dad, you think everything your daughter does is a miracle. When she got to 38, I was thinking, wow, 39, if you just understood the trends a little bit deeper, 39 would be obvious to you, right? And then in the same story as I'm telling students, I ask them, the students, what would you think if I told you I could count to 39? Would you be impressed? And they, of course, say no. And I say, what would you think if I told you I could count to 339? And of course, the answer is almost, it's still no, and the question becomes almost silly, but it makes, I think, an important point, and that is that it's not really that difficult to count to 339 if you understand the trend, right? So I didn't look at my daughter and say, I'm disappointed in you. You can't do something that's easy. I didn't say that to her, of course, right? I was delighted that she could do that. But I wasn't necessarily satisfied. My goal was for her to be able to count to 39 someday, and then 49, right? And so my goal is the same for you. And that's why we're talking about this section, carbonyls as electrophiles, because we're going to talk about the trends. And we're going to map it over to things that you do already know. For example, you already know that if a carbon has 3 electron groups coming off of it, it's planar. It's trigonal planar, really, right? It's trigonal planar. And we also know that if you can make up valid Lewis dot structures with the same connectivity but different distribution of electrons, then you have something called resonance. Resonance is a huge deal. We've already talked about why it's so big and what it means in organic chemistry. But it turns out that resonance is going to matter here. So what you have here is a polar bond, an electronegative element, right? An electronegative element right there. That means he's pulling the electrons that way, the bonding electrons. Well, turns out that oxygen has the capacity to manage a negative charge. Now, it's not super stable, right? But it is a significant contributor to the resonance hybrid. So, please draw out the resonance hybrid. Pause the video here and now, and I'm going to draw out the resonance hybrid. You pause it now and beat me to it, and come back and see what I've drawn. Okay, I'm going to suppose you paused it, and I'm going to say, right, there's a carbon here, and a carbon here in both of them. 1, 2, 3 carbons. Okay, so I've got 3 carbons here. There's an oxygen in both resonance hybrids, so there's my oxygen, right? There's 2 lone pairs of electrons in both of them. So I'll see, there's my 2 here, and there's my 2 here, right? All right. Now now it becomes tricky. The carbon is neutral here and positive over here, so that makes this somewhere between. The oxygen is neutral here and negative over here, so that makes this somewhere in between. Okay? So I've taken care of that, Oh, and there's one more thing. This bond is a double bond here and a single bond over here, so that makes this somewhere in between. Okay? Now, a good question would be, what is the bond order of that bond right there? Bond order. What's the bond order of that bond? Is it a single bond? Is it a double bond? Is it half and half? No. This is more stable. This is the more stable contributor. So it's closer to 2. So we would say that the bond order is between 1.5 and 2. Right? Because this has a greater contribution to the resonance hybrid because it's more stable. All right? So again, there's a minor but significant contributor that looks like this. Minor but significant. Okay, we've got 9 slides to get through, so I'm going to move on. This is a big deal. Okay, so another factor that we've got to take into consideration is that the carbon is partially positive because of induction. So this is what I drew on the previous slide, right? We already know that those oxygens are drawing off even the sigma electrons. They're pulling it that way because that is an electronegative element. Electronegative element. Okay? Because of induction. And then finally, it's a good it's important to know that this is a good target because of its shape. It's trigonoplanar. All right? And since it's trigonoplanar, it's a beautiful target. All right? So, consider these factors. Resonance, induction, and shape. Which should be more reactive as an electrophile? Aldehydes or ketones? And explain why. Which should be more reactive? Aldehydes or ketones? And consider all 3 of these: resonance, induction, and shape. Okay, so compare these 2. Let's name this. 1, 2, 3. Actually, no, it's the other way around, right? 1, 2, 3. So it's propane. Aldehyde. Propanal. I don't have to say 1 because it's always at the end. And it looks like it's 2,2-dimethyl. Propanal. All right, and this is not. It's something different. We can do that one too, I guess. 1, 2, 3, 4, 5. So this is 3 pentanone. I told you I was always going to do that, right? 3 pentanone. So it looks like it's 2, 2, 4, 4, tetramethyl, 3 pentanone. All right, which is more reactive? And I'm not going to answer that. I don't know if I said I was going to a minute ago or not, but I'm not going to. You bring that question to class. That's a good question. All right, finally, well, not finally, we have several slides to go. We want to analyze how nucleophiles attack carbonyls and why some nucleophiles react and others don't. So here's a good example of a nucleophile, right? You got a lone pair of electrons, formal charge, flat, electron poor, carbon, bam, these guys go up, right? Wow. Now, if the nucleophile is weak, or if the attacking nucleophile is a good leaving group, the reverse reaction will dominate, right? Because we have a formal charge up here of -1. So these electrons, which really should be coming from a lone pair of electrons here, right? Coming down, boom, good leaving group. Excellent leaving group, right? Because it's huge. Good leaving group. So this is going to predominate. So this was if this was equilibrium, and it is, then it might look like this, right? Okay, now show nucleophilic attack for some other nucleophiles and do all of these. Cyanide, hydride, alkanide, I think is what they call that, and water. When the nucleophile attacks, is it resulting in immediate stable or unstable? Why? If a nucleophile is also a good leaving group, it's likely to react with the carbonyl. Is it likely? Explain why. I'm not going to answer any of these for you. You need to stop the video and look at these questions. And they were answered in previous slides. Okay? Consider this. There's a lone pair of electrons in each of these, and I'm going to show where it is. And do those. Do all 4 of those. Bring those notes to class with you. Okay. So here's an example of a general example. If the nucleophile is strong enough to attack but not a good leaving group, right, there's not a good leaving group, then bam, and these guys go up here, wham, and you have, and this is what you get, right? Super intuitive if you understand electrons. All right, and then we get a proton transfer, and boom, there's your result. Okay, now the intermediate carries a negative charge. So generally speaking, we want to pick up an electron. Okay, if the nucleophile is weak and reluctant to attack the carbonyl, how can we improve this? Good question. We can make the carbonyl more electrophilic. So this is one way we can do. Look at this. If we want to make that more, so it starts out with a partial positive, but we want to make it really like a big partial positive. How are we going to do that? We draw electrons off. Watch this. Very common. You've already seen this some in other parts of the course. This is incredible. How are we going to make it more electrophilic? Adding an acid will help. How? How does that help? Okay, now again, I'm going to ask you, draw the resonance hybrid. Okay. So what happens is you get attack of a proton. This is just proton transfer. You've seen it a bunch of times. Then the nucleophile comes in, boom, and you get the same results we had before, but the proton transfer happens earlier. Okay, let me give you a hint. Some of these happen in basic conditions. And some of these happen in acidic conditions. Watch out for that. Okay. Is there a reason why acid is not used with strong nucleophiles? Right, suppose that we have a strong nucleophile. There's 2 reasons really, right? One reason is that if we've got a strong nucleophile, it doesn't need any help coming in. Right? And there's one other reason.